Not a one? Yes.
Who built the particle detector?
Who builds?
So highly specialized. Well, this is like a big market for that kind of thing.
Oh, yeah. You probably noticed that papers from the LHC have about 3,000 authors. So this is actually a measure of the size of the team that it takes to build one of these giant detectors. This SLD detector, which I had on the first slide yesterday, the group is about 300 or 400 authors. So that is a group of, I think, something like 20 or 30 universities from the US, Japan, Italy, England. I forget whether there's a French contingent in SLD. Basically, what you do is you start out with a relatively small group of people who try to design the detector. And I emphasize that these detectors are very modular. So they come in components that eventually are supposed to fit together into a whole. Then the responsibility for those components is taken by different university groups or laboratories. For the really large components that require major engineering, typically those are national laboratories. And for the smaller components, they can be built by individual university groups. So often, like the big thing like this, which is a big gas chamber that does tracking, will be put together by a national laboratory. In SLD, that was actually built at Triumph. And then the big iron frame of the whole thing was commissioned by SLAC, where the detector was located. It was actually ordered from Kawasaki in Japan and delivered on boats and assembled at SLAC. Then some of the smaller components, particle identification, the electronics modules, things like that, were built at individual universities and then transported to SLAC for final assembly. So, when you're talking about one of these major detectors, it's really a worldwide operation, parts coming from all over the world to the accelerator laboratory. And, of course, they all have to fit together, which is quite non-trivial. Just administratively, it's a huge enterprise. Of course, for the LHC detectors, it's even more complicated. You have literally groups from almost every country that has serious physics in the world, individual universities building components, and then these all have to fit into some big package that, as I said, is like a many-story high building. So it's totally non-trivial. And then you have to actually get the signals out. So, for Atlas, for example, there are 10 to the 8th electronics channels running out of the detector. So you better not have two cables that are plugged in the wrong way. Otherwise, you're not going to understand what's going on. And a lot of work goes into checking that, all the cables are right, the number of dead channels is minimized, every channel has to be calibrated. It's just a huge effort. How many of you have participated in this? One? Okay. So participating with an experimental elementary particle group. So you go and calibrate some piece of apparatus. Yeah. So I think you understand that you're just a tiny piece of some huge operation. Nevertheless, it's not. In the end, it's not industrial physics. When these collaborations are well managed, graduate students can have ideas and work with the data creatively, and ideas can come up from the bottom. It's a major challenge, though, to keep it from being, people in white coats who are not allowed to think but just have to do what they're told. And I think a lot of credit has to go to the management of these collaborations to allow a more, free-flowing intellectual structure. I don't know, I'm a friend of Fabiola Giannotti, who's the head of the Atlas collaboration, and she's someone who really has the right spirit in this respect, giving a lot of respect to the people who were on the ground floor trying to have good ideas about what to do with the data. But that's also part of it. I mean, you need, administrators who really know how to lead scientists rather than just say this is what has to be done. Okay, other questions? Yes? I'm sorry? Well, the interpretation I gave you yesterday is that strangeness is the property of having a strange quark. So the S quark, or strange quark, we assign strangeness 1. And from that, you can construct the strangeness of all the particles that I wrote up there. So for example, a sigma baryon has 1 S quark, so it has strangeness 1. The omega minus baryon has 3 S quarks, it has strangeness 3. The K plus has an anti-strange quark, so it has strangeness -1. Now, why should strangeness be conserved? Well, strangeness isn't really conserved by the standard model. It's conserved by the strong and the electromagnetic parts of the standard model. Another way of saying that is that the photon doesn't conserve strange quarks. It doesn't allow a strange quark to turn into another kind of quark by emitting a photon. Similarly, we'll see when we discuss strong interactions, the same is true for gluons. The gluon coupling to a strange quark always ends up with a strange quark. So you can have a gluon or a photon that makes a pair of a strange anti-strange, but that also conserves strangeness. Now, the weak interactions don't conserve strangeness. A W boson, or a weak interaction, can turn a strange quark into an up quark. Now, how does that all fit together? Well, in the last week of the course, I'll try and explain that. Okay. Other questions? Yes?
Why don't you say that something does happen or doesn't happen because of the conservation of strangeness?
Yes?
Isn't it like the other way around? You see that certain processes like are forbidden?
Oh, absolutely. In fact, that's why we say strangeness is conserved. There are lots of processes that happen and other processes that don't happen. And there's this principle, everything that doesn't happen for a reason. Right? It's not only things that do happen that happen for a reason, but if something is forbidden, it should be forbidden for a reason. And so people tried to codify that, in particular Gelman and Nishijima, codified that by assigning this quantum number called strangeness. So that explained why a lot of things that you might think happen, like, you might think that you could have a reaction where a pi plus and a proton could turn into a sigma plus and a pi zero. And this doesn't happen. And so people codified things like this by saying that this violates the conservation of strangeness. But then ultimately you have to ask, well, why is strangeness conserved? Well, then it goes back to the conservation of the number of strange quarks. Well, why is that conserved? Well, then we have to go and look in the standard model and see what it says. But yeah, ultimately you start with the experimental data and you try and figure out what's going on from there. Okay. Okay, so where we left off yesterday was the discussion of particle detectors. And there are just a few more things that I want to say about that. So looking at a particle detector end on, what I said was that typically there is some kind of tracking region where you image the tracks of charged particles and a magnetic field that bends those charged particles so you can measure their momentum. Then I also told you that outside of that region, you have some devices that try and catch particles and measure their total energy, the so-called calorimeters. And there are two types of calorimeters which work on two quite different principles. The first one is an electromagnetic calorimeter. So if you look at the energy loss of, well, let's say in particular an electron in matter, as a function of energy, there are various regimes. First of all, an electron or another charged particle going through matter has a regime where it does ionization. It goes through material, it kicks out soft electrons, it loses energy. Then what we saw is that that goes down, and there's a region which we call minimum ionization, where the particle is basically moving through almost at the speed of light and just jouncing the electrons off. But then when you come to an energy which is comparable to the mass of the particle, there's a new effect that comes in, which is pair production. So for an electron, you can have a situation where, well, maybe the simplest place to start is for a gamma ray, a photon, you can have a set of Feynman diagrams like this, where, and the other way around, where the gamma ray comes in, it sees the Coulomb field of some nucleus. It exchanges a virtual photon with that heavy nucleus, and that allows the energy of the photon, with some momentum taken up by the recoil of the nucleus, to turn into an electron-positron pair. And this is an effect that sets in when the photon has an energy of greater than 1 MeV, so you have enough energy to make a pair. At roughly the same time, an electron can interact with a nucleus and radiate a gamma ray whose energy is comparable to the energy of the original electron. So this process is called pair creation. This process is called Bremsstrahlung. And these two processes have, well, roughly equal cross-sections when the electron and the gamma ray have energies that are well above the electron mass. These processes, of course, depend on some momentum being taken up by the Coulomb field of by a nucleus. The probability of exchanging this photon is proportional to z, and so the cross-section is proportional to z squared. And so there's a big advantage here in having heavy elements like lead to stimulate this process. So this is the principle of an electromagnetic calorimeter. The probability is usually described in terms of what's called the radiation length. So that's a quantity called x0, which is given by the following formula. 20 roughly times alpha times the classical electron radius squared times the Avogadro's number divided by the A of the species, and then z squared has to come into this, the nuclear charge. The radiation length is something like 19 centimeters in copper. It's 1.8 centimeters. Sorry, it should probably be 1.9 centimeters in copper, 1.8 centimeters in iron, and half a centimeter in lead. So if you want to have a lot of radiation lengths, you want to go to the bottom of the periodic table and pick up elements from there. Basically, what happens now is the following. Let's say you have a lot of lead, and you have a gamma ray come into that, or an electron. It really doesn't matter after the first couple stages. Then, in the first half a centimeter, this will turn into an electron-positron pair. If these guys are relativistic, in the next half a centimeter, each of those particles will Bremsstrahlung a photon. In the next half a centimeter, these guys will pair produce, and these guys will Bremsstrahlung photons. And before long, what you have is a huge, what's called electromagnetic shower, that contains large numbers of high-energy gamma rays, electrons, and photons. And the shower continues until the particles reach something called the critical energy. The value here, I think, is 800 MeV divided by the Z of the species. So for lead, this is something like 100. So when particles come to a few MeV, then ionization is larger than these pair production and Bremsstrahlung cross-sections. And then you go back to your ionizing particles again. But as long as you're very relativistic for an electron or very much above 1 MeV for a gamma ray, what the main process that's happening is you're producing more and more of these gamma rays and electron-positron pairs. And so what happened, and please notice that in every half a centimeter, you're significantly lowering the energy of the particles. So you start with one, let's say, 300 GeV gamma ray, and in some number of centimeters of lead, you've broken that all down into hundreds or thousands of electrons, positrons, and gamma rays. Okay. One more important quantity is the width of this shower. That's described by something called the Moliere radius. And that's basically given by the radiation length times 21 MeV divided by the critical energy. So the shower, if you like, has a definite length, which is related to the energy. Basically, it grows as the logarithm of the energy. It has a definite width, which is called the Moliere radius. And within that region, all these particles are produced. Now the question is, how do you visualize this? And the typical way to do that, of course, you can't visualize anything that's happening in lead, because that's just a big block of stuff, is to segment this in some way with an active medium. And so typically what you would do then is to build this out of pieces of lead together with some kind of active medium, either plastic scintillator or I think what's done in Atlas is you have the lead pieces in a bath of liquid argon, and then the ionization will drift in the liquid argon to some electrodes, and you measure it. What that means is that such a device samples the large number of electrons, positrons, and gamma rays that are produced in the shower. And typically, the resolution of the device is given by its ability to sample the shower. So the main source of experimental error is the fact that you don't see the whole shower, but you just see some kind of statistical sample of the shower. And so the typical kind of expectation for electromagnetic calorimetry is something like 10% over something that will go down as the energy increases. If you think about sampling, you're taking some random sample of the population. And so I think the expectation is that this should go down as the square root of the energy that you're trying to measure. So with energy in GeV, this is a reasonable estimate of what you expect in an electromagnetic calorimeter. Typically, there's also some constant term. I think in Atlas, the expectation is 10% over root E plus something like 0.2%. Just an overall term which represents basically your other uncertainties which are not dominated by sampling, your ability to measure things, to collect all the charge, etc. Now, the other large LHC experiment, which is called CMS, uses a somewhat different technology. They have large crystals of a stuff called lead tungstate. Now, think about this for a moment. Lead is at the bottom of the periodic table. Tungsten is at the bottom of the periodic table. This compound, though, is a crystal. And actually, it looks like a transparent crystal, except what it actually is a piece of material that's as heavy as a lead brick. And then you can dope this with a scintillator. So light will go, so throughout it, you detect ionization, you make light. It goes through this crystal, and it's read at the back by a photomultiplier. And people argue a lot about what is the trade-off between these schemes. If you have a crystal, the light can come from anywhere. So you don't resolve the depth of the shower, but you do better than this 1 over the square root of E in terms of the resolution. In this technique, you do more poorly in the resolution because you're seeing only a small part of the shower, but you can actually watch the shower as a function of depth, which has other advantages. And so that's one of the ways in the LHC era that Atlas and CMS will play off against each other. We'll see who'll win in the various categories of particle detection. Okay, so the problem with this is that this only works for electrons and photons. Muons, of course, go through the whole thing. For muons, for pions, the same physics occurs, but the energy at which pair production starts is a much higher energy. Not 1 MeV, but hundreds of MeV. And so typically, in the whole regime that you're talking about, the electromagnetic effects are subdominant. What dominates are just, first of all, radiation for muons. Occasionally, a muon will produce 2 more muons or electrons, a so-called trident process. But that's very subdominant in a detector that's only meters large. For pions, the other thing that will occur is that pions can hit nuclei and interact through the strong interactions. And so what you can have then, so again, here's the interaction point. Here the charged particles are coming. So you have your tracking volume. Then you have your EM calorimeter, which, as we've emphasized, is maybe a meter thick, will seriously contain this shower. And then out here, you have some other region where pions, which can basically get through this with relatively few interactions, will interact with nuclei much more sparsely, and in that way degrade their energy. And once again, you have to sample in some way because you need material to make the interactions, and then you need some other thing that will help you visualize the interactions. So now, what are the length scales up here? Well, those are given by the interaction distance, which is basically 1 over the interaction cross-section times the density of the material. And typical interaction distances are much larger than the ones that I wrote before. 39 centimeters in copper, I think 18 centimeters in lead. And actually, sorry, and comparable to this in iron. Yes?
How do we actually measure the energy density positive?
I'm sorry?
How do we measure the energy density positive in the calorimeter? Because we say if you sample it, we just see a track of the shower.
In fact, you see less than that. You see some ionization. Right? You see a region that's lit up in some way.
And how do we extract?
Well, then you have to model this. So you know what all these cross sections are. So you make a model, a computer simulation of a shower, and then you figure out from that computer simulation how much ionization you expect. And then you measure the ionization, and then you play those against one another. So there are some quite sophisticated codes that will propagate photons and electrons through a stack of lead and scintillator or lead and some other material. And then you use those codes to emphasize what signal, to estimate what signal will come out from a given photon or electron that goes in. And very often people will take a model of their detector and put it actually in a particle beam and check whether the simulation is correct. So yeah, it's not trivial. But roughly, the amount of light that's coming out is proportional to the energy. Yes?
How do you originally calibrate the software?
Sorry?
How do you originally calibrate the software?
Well, as I said, you can build something, put it in a particle beam of a known energy. For example, electrons from a linear accelerator, you know what their energy is. And you see what signal comes out. Actually, for the, you guys know what the Fermi Gamma Ray Space Telescope is? So this is this thing that's going around in space now, measuring gamma rays from active galactic nuclei and such. they actually took a module of the electromagnetic calorimeter from Fermi and put it in a tagged photon beam at CERN to check the very sophisticated Monte Carlo that they wrote for the performance of this thing. Okay, so in any event, these distances are much larger than the distances involved in electromagnetic calorimetry. And also, hadronic showers from hadronic interaction fluctuate much more. In this process here, nothing comes out but an electron and a photon. But if a pion hits an atomic nucleus, various things can come out. You could have a pi plus come out and other stuff. Or you could have the leading particle be a pi zero and other stuff. If it's a pi zero, this immediately decays into 2 photons, and all of the energy is released in a very small region. If it's a pi plus, this is going to fly another 20 centimeters before it interacts. And so this very different response to charged particles and neutral particles contributes a significant amount of experimental error to measurements in hadronic calorimetry. So just for comparison with the number that I wrote before, in ATLAS, the hadron calorimeter is expected to have a performance of something like 56% over the square root of E, as opposed to 10% over the square root of E, which I wrote before for an electromagnetic calorimeter. Again, the square root of E behavior depends on sampling. And so, and maybe I should also say, the hadron calorimeter in ATLAS is 5 meters of iron. And even that doesn't fully contain the highest energy showers. Okay, well now you have to put all these things together, and as I guess I'd like to emphasize, there are all kinds of compromises when you do that. So in, let's see, those figures that I asked you to look at, sorry, what page is this page? Could you tell me? Sorry? 15? Okay. Turn to page 17, and you'll see the layout of the SLD detector. And on page 18, you see the layout of CMS. And you can see in these figures some of the compromises that are made. A superconducting magnet is often a radiation length or 2 thick. And so you don't want to put a superconducting magnet in front of an electromagnetic calorimeter, because then the action in the first few radiation lengths will be invisible to you because it's going on inside the magnet. On the other hand, if you put the magnet outside the electromagnetic calorimeter, it has to be enormous, and you probably couldn't afford to buy it in the first place. So SLD is relatively small. They put the liquid argon calorimeter, the electromagnetic calorimeter, inside the magnet, but they put the hadron calorimeter outside the magnet. The tracking stuff is in the bottom right-hand corner. The thing called a drift chamber is a gas chamber, so that's a relatively thin device. They also put in there a device called the Cherenkov ring imaging detector that takes up a huge amount of space and does almost nothing for the purpose of the experiment. Don't ask me why they did that. In CMS, there's a somewhat different kind of compromise that are made. First of all, they have the tracking device have all the silicon in it, which is very good for reasons that I explained in the last lecture, but it also costs you about 2 radiation lengths before you even get to anything that's measuring electromagnetic energy. So electrons and photons have a very high probability of making pairs or Bremsstrahlungen just in the tracking part before you get to the electromagnetic calorimeter. Then behind that, they have these beautiful crystals that I explained to you that do a fantastic job of measuring electromagnetic energy, provided that there's still something to measure when you've gotten out to that distance. Then they decided to put hadron calorimetry inside the magnet. So to do that, they used copper, and it's a fairly coarsely segmented hadron calorimeter. And then they have their large magnet, a 4 Tesla superconducting magnet, as I said, almost the size of this room. And then outside that, iron and scintillator, which does several things. First of all, it gives you more magnetic field, which is bending power for the muons. And it also, as we say, is a tail catcher. It catches the end of the hadronic showers that punch through that copper and punch through the magnet and get into the outer regions of the detector. So ultimately, all these things have to be integrated in some way. And what people always end up doing at the end of the day is you make a huge simulation of particles that propagate through all of these layers, figure out all of the signals that a particle you're interested in should make, and write some software that tries to integrate it and get the best possible measurements of energy and momentum. So that last figure in here just gives you a kind of overall glimpse of what CMS looks like in terms of its ability to identify different kinds of particles. And I think if you've understood this lecture, you'll be able to just go through that and look at the different particle types there and see that they're being, if you like, caught in the right place. And I'm happy to answer any questions you have about that last figure later. OK. Yes? Sorry, muons? Well, muons, as I said, are basically not interacting. They're just making tracks and going through the whole thing. And so then you just have to have enough B squared L, enough magnetic field times length, to bend the tracks enough that you can actually see the bend and measure it precisely. Now, you probably know that in Atlas, they have this, they have a detector with a 5-meter radius, and then there's another, I think, 3 or 4 meters that has a toroidal magnetic field. So the idea is that the particles come out, they bend this way in the internal magnetic field. Then they go through this many meters of calorimeter. Most of the things that get through that are muons. And then they bend in a perpendicular plane in the toroidal magnetic field. So you have actually 2 measurements, 2 different independent bending measurements for a muon. And this one is the best for the low energy muons. This one is the best for the TeV energy muons. And then you try and put them together to get a good compromise. So you get a few percent over the whole large energy range of the device. OK. OK, you guys are totally exhausted with experiment. You want to do some theory, right? OK, so let's get to that. OK, now, last year I just jumped into this. But this year I think I realized I've got to do something different. The place that I wanted to start is by telling you a few things that actually I hope you already know, but probably you don't, about quantum electrodynamics. So a very good place to start trying to talk about the strong interactions is to think about the process where you start with an electromagnetic probe and you end up with hadrons in the final state. So I want to spend a couple lectures talking about the process electron-positron annihilation to hadrons. So hadrons means pi plus pi minus, pi plus pi plus, pi minus pi minus, pi 0, just any number of pions and kaons, protons, antiprotons that come out in the final state. And it turns out to be much more interesting, rather than studying these processes one by one, to study them collectively. So you saw this picture that I showed you, that when you have at 91 GeV, electron-positron annihilation, I said, to quarks, what it looks like is a big mess with lots of particles coming out. And so it turns out to be more useful than looking at each individual final state to think of those things collectively and to try and learn about their properties. Now, a very good starting point as a reference is to think about a much simpler process, which is the process of purely electromagnetic pair production. For example, E plus E minus to mu plus mu minus. Now, I think you guys did calculate the cross-section for E plus E minus to mu plus mu minus in Zarembo's course. OK. But that was in 2010. And it was also your first encounter with field theory. So I think the first thing I'd like to do is to remind you of how probably he did it, and to redo the calculation so we get some formulae that are fresh in your mind. So now we're going to do a kind of lightning review of things you learned in your quantum field theory course. And I guess what I'd like you to do is I'm going to go through this relatively quickly, and I'd like you to slow me down if there are points that you didn't get last time or that Zaremba didn't discuss. Okay? So what I'm going to do now is to compute the differential cross-section for this process from scratch, but maybe since you've seen it before, it'll be review. Okay, so this process is very simple. It has one Feynman diagram. That Feynman diagram, I like to draw Feynman diagrams with time going this way, has an electron annihilating a positron. A mu minus comes out, and a mu plus comes out. And I'll label the momenta P, P bar, K, and K bar. And we can write down the value of that Feynman diagram. Two electromagnetic couplings, one propagator, let's call this momentum here Q, U bar of K, gamma mu, V of K bar, V bar of P bar, gamma mu, U of P. Okay, everybody's happy so far? Good. Okay, now what I need to do is to turn that into a value of a cross-section. Now, you all know what a cross-section is, right? It's some measure of the interaction probability of two quantum particles. And I think Zaremba derived for you this formula for the cross-section, which, of course, you've all committed to memory, I hope, that if A and B collide and produce something, the cross-section is given by a flux factor, 2EA times 2EB times the difference in the velocities, the integral over phase space, and the square of the matrix element. And this is true for each individual quantum process. So if you have particles with spin around, you have to sum over the spins that appear in the final states. And in the initial state, you have to do what's appropriate. If you have unpolarized beams, you have to average over the spins. And if you have polarized beams, you should put in the correct polarization. So everything on this board, I hope, is totally familiar to you. And if it's not, you should complain now. And I don't see anybody complaining. But don't be shy about it. OK, so now I'd just like to simplify this expression a little. First of all, in this course, we're always going to be talking about very high energy processes. So everything's going at the speed of light. So this number here is always 2. We're always talking about energies that are much larger than the mass for the initial state particles. So this thing is roughly ECM squared, and this thing is going to be 2. For this process, I'm going to talk about two-body phase space. And Callum has assured me that this expression you've seen derived, two-body phase space is 1 over 8 pi. And then if you have massive particles in the final state, twice the momentum divided by the center of mass energy. So if I put in all of those simplifications, and by the way, if you have two equal mass particles in the final state, then this becomes 1 over 8 pi, or maybe I should write it as the integral d cosine theta, 1 over 16 pi times k over m, k over e, where this is the momentum of a particle and this is the energy of the particle. And so now I'm going to write this formula, and I actually do expect you to memorize this formula. So this is for A plus B going to 1 plus 2, where these guys have equal mass. And I'm looking at the differential cross-section with respect to cosine theta. Okay. So if you haven't seen it in exactly this form before, this is a very useful expression. And yeah, it's one of those things that you really should commit to memory. Okay. You're all happy with this, right? Sorry? The total center of mass energy. Okay. So ECM, in this case, is equal to 2E, is the total center of mass energy. Okay. Good. Yes?
We didn't actually go into detail in, say, deriving the Feynman rules for QED.
Ah.
So,
Okay, well, that's not so hard. This is equal to minus IE gamma mu. Right. So the current has a gamma mu in it. And when you strip off everything else, this is what's left.
okay, and why is there a U bar and then a V and then a V bar and then a U?
Ah, because the U bar is associated with the producing a particle. The U is associated with annihilating a particle. The V bar produces an antiparticle, and the V annihilates an antiparticle. So this is exactly for the mu minus, the mu plus, which come out, and this is for the E plus and the E that go in. Yes?
Sorry, what exactly is d pi when you write it like that?
Oh, this is the integral over phase space. So the integral d pi is equal to the product over the final particles. For every final particle, an integral over their relativistic phase space. And then for all the particles, an energy momentum conserving data. Okay? And Zaremba derived this expression for you, I think. And it's very useful. Phase space is really important when you do elementary particle phenomenology. So it's good to understand it. And in particular, not only two-body phase space. So on the problem set, I gave you a problem about three-body phase space, which I hope you'll find very interesting. But for today, only two-body phase spaces. Actually, one of my research problems is to generate n-body phase space for huge arrays of quarks and gluons. So I think even there are things that people haven't found out yet that are interesting. Okay. Anybody want to be brave and ask me a question about anything else on this blackboard? Okay, we're doing good. So now what I'd like to do is to take this formula, which by now you have all committed to memory, and to use that formula to evaluate the cross-section that comes from this Feynman diagram. So now you all know how to do that. Or, well, we'll see if you remember how to do that. So the main thing that we need now is the square of the amplitude. And what I'd like to first do is compute the square of the amplitude summed over all polarizations. To do that, I need to use some identities like UU bar, the sum over polarizations, is P slash plus M. And for VV bar, the sum over polarizations is P slash minus M. And so if you square this expression and sum over all polarizations, you get the following thing. E to the fourth over Q squared squared. If I start from here, K slash plus M, gamma mu, K bar slash minus M. If I complex conjugate, I need a gamma matrix with a new index. Let's call that nu. And if I connect the Dirac indices around like that, I'm taking the trace. And similarly for the initial state, if I start here, I have P bar slash gamma mu, P slash gamma nu. and once again taking the trace. Did Zaremba do things like that? Yes? No? Yes? Yes or no?
I don't remember it.
Okay. Let me just describe this ingredient here. This ingredient is V bar of P, gamma mu, V of P, just this element, U of P, this element here. And then we square it, so I have to multiply by the complex conjugate. Okay. Now I need a new dummy index here, so let's call that new. Now I want to sum over the spin of the electron, and I want to sum over the spin of the positron. The sum over the spin of the electron, I use this identity, and I have P slash. I'm ignoring the mass of the electron, by the way. Gamma nu, gamma mu. And if you think about moving this guy around to the front, it has this identity, and there's a P bar slash. And then finally, this gamma is connected to this guy. This gamma is connected to that guy, so all the indices connect up. This is a matrix. And I need to connect up the back and the front index, so I would do that by taking the trace. And that's a derivation of this element of the formula that I wrote. And this one you can derive in the same way. I'm just keeping the mass here. Okay, very good. Okay, so now it turns out that these expressions are very simple to evaluate. Yes?
We are making the mass of the electron 0, right?
I'm making the mass of the electron equal to 0. Yeah, I'm interested in producing muons. The muon has a mass 200 times the mass of the electron. So if the muon mass is important, the electron mass is negligible in the first approximation. It'll just make the formula simple. Okay, so now we need to evaluate this expression. And long ago, Feynman taught us how to do that. So the basic idea is to use the identities like this. The trace of gamma mu gamma nu is 4 G mu nu. It's got to be proportional to G mu nu, because what else can it be? And if you take the square of a gamma matrix, that's 1. So if I were to trace this formula, and gamma matrices are 4 by 4. So if you just take the trace of the formula, you'll see that it's correct. Did Zaremba do that in his course? Yes. Okay, and he probably then also wrote down for you this formula. Which you can derive from the formula above using the Dirac anti-commutation relation. And those are the only formula that I'm going to need from this study to do this exercise. Okay. Well, now we're totally in business. Let's first evaluate this object. So we just use this formula. The last term gives something symmetrical here. The middle term gives minus G mu nu P dot P bar. So far, so good? Now let's evaluate the other formula. Okay? Now I just dot these two expressions into one another. There's the 16. With that gives something like p bar dot k plus times k bar dot p. And then there are two ways to do that. That'll give it, and this will give it. And the other way around, I'll get the other combination. Now, that times that, and that times that will give minus 4 p dot p bar k dot k bar. That times that will give plus 4 p dot p bar k dot k bar. So those two terms conveniently cancel. The m squared times that will give minus 2 m squared p dot p bar. And the m squared times that will give plus 4 m squared p dot p bar. And now we're done. We come to the following very convenient expression. 16 times, let me pull out a factor of 2, 32 times p bar dot k times k bar dot p plus p dot k, k bar dot p bar plus m squared p dot p bar and another factor of 2. So far, so good. Sorry? Oh, you're right, I did. Okay. So far, so good. So now, what are you supposed to do with an expression like this? Well, I'm going to tell you other things you can do with this expression in just a moment. But right now, let's just do the most straightforward thing with it. Once you get an expression like this, the next thing that you're supposed to do is you draw a picture of the reaction with all the kinematics labeled. And then you plug into this formula appropriately. And then you pretty much write down the answer. And to write down the answer, we need to use this expression. But since you've already memorized that expression, I'm going to erase it. So here's our picture of the reaction. An electron and a positron go in. This one has momentum P is equal to E, 0, 0, E. This one has momentum P bar is equal to E, 0, 0, minus E. The muons come out with an angle theta. This one has momentum, the same energy E, 0, 0, P, where P is equal to E squared minus M squared. Okay, well now it is appropriate to take the speed of light equal to 1, and I'm going to do that throughout the rest of the course. I'm also ignoring H bars everywhere in case anyone worried about that. And this momentum vector down here is, oh, sorry, I didn't write that right. P sine theta, P cosine theta. And this one, the mu plus, has vector 0 P sine theta minus P cosine theta. And I've made a specific choice of the orientation of the muon pair, but it's not going to matter. They'll be isotropic in the azimuthal direction around the beam axis. Yes? Did you have a question? No. Okay. So now we just take these expressions and plug them into here. Sorry? Oh, no, I'm sorry. It's a slightly confusing notation. P here is a 4-vector, which is the 4-vector of the electron. Its components are only E, the energy of the electron. This P is the momentum of the muon in the final state. Maybe I should call it K instead. Thank you. Okay. So now we can just evaluate these expressions. So this is 32 times E squared plus EP cosine theta. That's the value of this quantity. It's also the value of this quantity. On the other side, I reverse K and K bar. So that'll give a minus sign here. And in the last term, P dot P bar is 4E squared, and there's an M squared. Sorry, 2E squared, and there's an M squared. Okay? And now we just have to put everything together. So let me extract one more factor of 2. E to the 4th plus E squared P squared cosine theta plus E squared M squared. Maybe it's convenient to write here cosine squared theta plus sine squared theta. And that I can combine with that. E to the 4th plus E squared P squared plus E squared M squared sine squared theta. And let me remind you that the center of mass energy squared is 4E squared. And this is also equal to the value of Q squared in the previous expression. Yes?
Do you think they could be K?
Yes, they should. Callum didn't correct me fast. And so finally what we get here is 4 times the center of mass energy to the 4th power times 1 plus, and there should be a cosine squared theta there. That's what I should. Cosine squared theta plus M squared over E squared sine squared theta. Okay. Well, that was easy. Half of you could probably do this in your head with some experience. Okay. Well, now all I have to do is remember the formulae that I memorized. And then let's do one more thing. What I computed was the sum over polarizations. But what I'd really like to compute is the average over initial polarizations and the sum over final polarizations. So if I average over the initial polarizations, that is to say I use an unpolarized electron beam and an unpolarized positron beam, I have to divide by 4, which is very convenient because there's a 4 there. So now we're done. D sigma d cosine theta is equal to 1 over 2 ECM squared times 1 over 16 pi times K over E times the square of the matrix element summed over initial and averaged over initial and summed over final polarizations, which is E to the 4th over ECM to the 4th times ECM to the 4th times 1 plus cosine squared theta plus M squared over E squared sine squared theta. And alpha is E squared over 4 pi. So that eats up most of the 16 pi very conveniently. And what we end up with now is this formula. Which is very simple. And let's see, K over E is 1 minus M squared over E squared to the 1/2, and now it's completely explicit. when E is much larger than M, this simplifies to an even simpler formula, 1 plus cosine squared theta. And indeed, if you do all the technological work of making an electron beam, and why don't you ask the question publicly?
I'm a bit behind. So where did that decay go in that line?
Which K?
64 e to the 4 plus e squared.
Oh, I'm sorry.
something like that.
K squared plus M squared is E squared. So this should have been an E to the 4th. So that and that combined into this.
Okay.
And this was left over.
Okay.
Okay. Good. Okay. So, good. So now we've done this complete calculation and we've got this result. And yes, indeed, it's true. If you do the work of making an electron beam and a positron beam, and you collide them together at a certain energy, and you build one of these detectors that I was describing, and you look for tracks that go all the way through a very thick detector, so they're probably muons, indeed, they have the angular distribution 1 plus cosine squared theta, which is an angular distribution that looks something like that. It's relatively smooth, but peaked in the forward and backward direction. Typically, you can't measure it, of course, all the way up to the beam direction, but you can measure it in some interval here, and this is a good fit to the final result. The normalization is predicted in terms of alpha. Everything is very nice. I'll tell you more about this formula next time, but for the moment, I just wanted to make one more point while I have some of these formulae on the blackboard. Did Zarembo mention the word crossing? Crossing symmetry. Okay. So this is something I'm going to use a lot in this course. And so it's a very simple concept, but I should define it. So on this blackboard, there's an exercise that I just erased where we took a formula like this that's written in terms of Lorentz invariant quantities. And I wrote it very explicitly in terms of the very explicit kinematics of the problem. Now, that's something that you often do when you evaluate Feynman diagrams. You start with something that's in terms of invariance, and you then go to the specific experiment that you want to analyze. You put in all the kinematics, and you get an answer of the kind that we got here. Now, let's say that you have a process that's given by a Feynman diagram like this, E plus E minus to mu plus mu minus. There's another reaction, which is E minus mu minus going to E minus mu minus, just the elastic electromagnetic scattering of an electron in a muon. That's given by this Feynman diagram. But if you look at it, they're the same Feynman diagram. It's just that the momentum labels are changed. But if I evaluate it in an expression that gives completely invariant expressions, I'm going to get exactly this expression with some appropriate change of the labels. Let's consider another example, which is E minus mu plus going to E minus mu plus, the elastic scattering of an electron in a positive muon. That's also exactly the same Feynman diagram, just with another interchange of the labels. And in each case, we're going to get, for the calculation that I just did, exactly this expression in terms of appropriately labeled momenta. So there's no need to do the calculation 3 times. Once is perfectly sufficient. You just have to keep track of the labels. And there's a nice way to do that. For a 2-particle process, we described one which is P, P bar, K, and K bar. Let's make everything symmetric by defining these momenta going out instead of in. Now I can define three invariants called Mandelstam invariants. K plus k bar squared, which, as you see by momentum conservation, is equal to p plus p bar squared. T, which is k plus this outgoing momentum, which is by momentum conservation equal to this one. And U, which is the other combination, which by momentum conservation is equal to the other combination. You can actually prove, in complete generality, that S plus T plus U is equal to the sum of the external masses. In the case that I was describing here, it's 2m squared. But in general, what you get is the sum of the external masses. The way you make that proof is that you add up this column, you use energy momentum conservation, namely k plus k bar minus p bar is equal to 0. And everything goes away except for the mass terms. So these are very convenient variables, and one refers to them all the time in thinking about two-body kinematics. In particular, this S is equal to ECM squared for the reaction I was describing over here. And usually in particle physics, you'll just see this written with S here. So whenever I write S, what I mean is the square of the center of mass energy. If I want to evaluate this process, then when I calculated the Feynman diagram, remember there's a 1 over q squared here. This thing is S for this process, it's T for this process, and it's U for this process. So we call this the S channel, the T channel, and the U channel. And in general, you can just look at a Feynman diagram and see where the singularities in the denominator are by looking at which way the propagators are oriented. So I'm going to be using, so the relation between these three processes is called crossing symmetry. And I'm going to be using crossing symmetry a lot in this course to make calculations easier. Namely, when we've done one, we can use crossing to do a lot more calculations just by relabeling things. And so that'll be something I'll do often. OK. This formula has physics in it, but I don't have time to discuss it. I'll go back to that and discuss it next time. Thank you. OK. Very good. Well, now you've heard it. Good. See you tomorrow.